If you record an observation that the length of a lab table is exactly 2, your statement has no scientific value. 2 what? Centimeters? Miles? By adding a single letter, the statement resolves. A physical quantity requires both a numerical value and a unit to be meaningful. This is the core formula for every physical observation in science. A measurement is always the product of a numerical value and its unit. The process of measuring is the comparison of an unknown physical quantity against a known, universally agreed upon standard. If your standard is 1 meter and a rod is twice that length, the rod is 2 meters. Because measurement strictly requires comparison, the validity of all physical science relies entirely on standardizing those base units. For centuries, societies relied on localized, arbitrary measurements, like the cubit, the handspan, or the foot. Competing models like the foot-pound-second and centimeter-gram-second systems made global scientific communication difficult. Translating engineering blueprints or research data between these systems was highly prone to error. To eliminate this friction, the General Conference on Weights and Measures adopted the SI system, the Système International d'Unités, in 1960. The SI system classifies every measurable physical quantity in the universe into one of 2 categories: fundamental, which are independent, or derived, which are dependent. This unified, decimal-based system provides the required mathematical grammar for international scientific progress. We start with fundamental quantities. These are independent variables that cannot be broken down further. They are the irreducible bedrock of physics. The SI system quantifies the complexity of the physical universe using exactly 7 fundamental base units. The first 3 govern mechanics, the meter for length, the kilogram for mass, and the second for time. The others handle thermodynamics, electromagnetism, and elemental properties, the ampere for electric current, the Kelvin for temperature, the mole for the amount of substance, and the candela for luminous intensity. For entrance exams like the IIT JEE, you can recall these using the mnemonic, "My king takes many cold apples kindly." Pay close attention to the kilogram. While we often work with grams in a lab, the official SI base unit for mass is the kilogram. It is also the only base unit that includes a prefix, kilo, in its name. These units are tied to rigorous physical standards. For over a century, this metal cylinder in France served as the real-world definition of the kilogram. Many of these quantities carry the names of foundational scientists, such as the Kelvin scale for thermodynamic temperature, named after Lord Kelvin. These 7 units are the irreducible building blocks of all physical sciences. Everything else is derived from them. Derived quantities are generated entirely by multiplying or dividing these base units. Velocity is the simplest derivation. Its formula, distance divided by time, maps directly to its unit, meters per second. Acceleration measures how velocity changes over time. Dividing meters per second by another second gives us meters per second squared. In dynamics, Newton's second law states that force equals mass times acceleration. By substituting our base units into the formula, we find that the unit for force is the kilogram meter per second squared. To simplify calculations and scientific communication, the SI system assigns special names to these long algebraic strings. We use the Newton as a shorthand alias for the kilogram meter per second squared. We apply the same logic to pressure, force distributed over an area. Dividing a Newton by square meters creates the Pascal. When you see named units like newtons or pascals, train yourself to mentally deconstruct them back into their base components. Understanding the structural algebraic formula behind these units makes rote memorization unnecessary. Consider the units for work, defined as force multiplied by displacement. Multiplying a Newton by a meter generates the joule. Because the Newton is already a derived unit, a joule is actually a nested string of base units, kilograms times meters squared per second squared. Power is defined as work done over time. Dividing a joule by a second produces the watt. This cascading chain, from base units to force, then energy, then power, shows how the system scales. These all represent distinct mechanical properties, yet mathematically they are simply different arrangements of mass, length, and time. There are specific exceptions within the SI system, particularly regarding how we measure angles. There are only 7 fundamental units, while the list of derived units is theoretically infinite. Angles are what we call dimensionless derived quantities. This is a frequent trap on physics exams.
The two primary examples are the radian for two-dimensional angles and the steradian for solid three-dimensional angles. They are dimensionless because they are ratios of similar quantities. Dividing an arc length in meters by a radius in meters causes the units to algebraically cancel out. Despite having no underlying base dimensions, these ratios still require a unit name for mathematical clarity. Identifying these dimensionless quantities is a critical strategy for avoiding errors in competitive physics. Every measurement is a numerical value multiplied by a standardized unit. The SI system provides a cohesive, universal algebraic grammar for physical reality. This algebraic foundation is the prerequisite for dimensional analysis, which uses units to track and correct errors in complex expressions. Even the most complex derived units can be untangled back to their fundamental roots. No matter how intimidating a new physics formula appears, it remains a balanced combination of the 7 foundational SI units.
In pure mathematics, 12.35 plus 4.2 equals 16.55. But in physics, writing that answer down is wrong. It must be rounded to 16.6. Pure math assumes numbers exist in a vacuum of absolute truth. Physics operates in the physical world. Every number we generate comes from an instrument, and as you can see in this macro shot of a polished metal surface, the physical reality is full of microscopic limits and imperfections. Because our tools have physical limits, the numbers they produce carry an inherent amount of doubt. We cannot ignore that doubt. We have to translate it into a strict mathematical constraint. This brings us to a foundational law of measurement. An equation's final output can never claim more precision than its weakest, least precise input. To enforce this properly, we need a framework. We will construct a mathematical pipeline that tracks how uncertainty originates at the mechanical limits of a physical tool, gets encoded into our data, and ultimately propagates through complex equations. Mastering this exact sequence is a strict requirement for advanced competitive physics and engineering problem-solving. In experimental science, calculating the numerical answer is only half the problem. Quantifying the exact boundary of your mathematical doubt is the other half. Let us start at the source of the data, the instrument itself. Every tool we use establishes a baseline limit of human observation. We call this limit the least count. It is defined as the absolute smallest value an instrument can measure with guaranteed accuracy. The least count dictates the maximum theoretical precision a physicist can extract from a specific tool. A standard meter scale is permanently capped at a least count of 1 millimeter. To push past that 1 millimeter limit, engineers designed mechanical solutions like the vernier caliper. This diagram shows how a vernier caliper generates precision by aligning two separate tracks. The least count is found by calculating the difference between one main scale division and one vernier scale division. If 10 vernier divisions match exactly 9 main scale divisions, a single vernier division equals 0.9 millimeters. Subtract that from a 1 millimeter main division, and you achieve a least count of 0.1 millimeters. For even tighter tolerances, we use a screw gauge. This instrument achieves higher precision by converting rotational motion into linear measurement. Looking at this schematic, the precision is determined by dividing the linear pitch by the number of circular scale divisions. A 0.5 millimeter pitch divided by 50 circular divisions yields a least count of 0.01 millimeters. Before a single calculation is ever made, the mechanical architecture of the instrument locks in a hard mathematical ceiling for precision. Once a reading is taken, that mechanical limit must be transferred to the page. We encode this limitation into our recorded data using the strict rules of significant figures. By definition, significant figures contain all the digits we know with absolute certainty, plus exactly one uncertain estimated digit at the very end. Take this measurement, 12.34 centimeters. The 1, 2, and 3 are certain. The final digit, the 4, is our first uncertain digit. Together, they give us a total of 4 significant figures. Counting them requires exact rules, especially concerning zeros. Leading zeros are mere placeholders. In 0.0056, the leading zeros do not count, leaving only 2 significant figures. Trailing zeros without a decimal point are also generally ignored. Writing 2500 indicates scale, but mathematically it only guarantees 2 significant figures. The critical exception is when a decimal is present. Trailing zeros to the right of a decimal point are significant.
Writing 7.000 explicitly indicates deliberate precision verified by the instrument. That gives us 4 significant figures. When we run these numbers through calculations, we inevitably generate excess digits that exceed our instrument's least count. We have to discard them by rounding off. If the discarded digit is exactly 5, we apply banker's rounding, known as the even digit rule. We round to the nearest even number. This ensures that half the time we round up and half the time we round down, which prevents systemic statistical bias from accumulating across large datasets. Significant figures are not arbitrary formatting choices. They act as the mathematical memory of the instrument's physical limitations. It is easy to assume that a highly precise number, one packed with significant figures, is automatically correct. That is a dangerous conflation. This scatterplot illustrates the difference. Accuracy is how close a measured value is to the true value. Poor accuracy is usually caused by systematic errors, like a warped ruler or a calibration defect, which push all readings off target in the same direction. Precision is the closeness of repeated measurements to each other. The tight grouping you see means high precision, even though it misses the true center. Precision is impacted by unpredictable, random errors, like small environmental fluctuations or human estimation. Systematic errors must be corrected in the physical world by calibrating the instrument. Random errors must be mitigated in the mathematical world by taking multiple readings and averaging them. To neutralize random error, we use the mean value formula. We take our dataset, x1, x2, and so on, and average them together. This mean, x bar, serves as our best mathematical estimate of the true value. We still need to quantify the spread. We calculate the absolute error for each observation. This is the exact distance of any single data point back to our calculated mean value. By averaging those distances, we get the mean absolute error. The final scientific result must always be written as a combination of the two, the mean value plus or minus the mean absolute error. Accuracy proves the instrument is true. Precision and error analysis prove how reliably that truth can be reproduced. Now we face the final escalation. What happens to uncertainty when multiple physical measurements are combined for algebraic formulas? The strict law of error propagation dictates that uncertainty always compounds. It never cancels itself out. Let us look at the propagation rule for addition and subtraction. An equation of z equals a plus or minus b yields a propagation formula of delta z equals delta a plus delta b. For additive operations, the absolute errors of the measurements are simply added together, regardless of whether the primary equation is adding or subtracting. When outputting the final value for these additive operations, the answer must be mathematically restricted to the same number of decimal places as the least precise measurement used. Multiplication and division requires a different approach. Here, z equals a times b divided by c. For multiplicative operations, you do not add absolute errors. Instead, it is the relative or fractional errors that add up. Finally, we have the power rule for values raised to exponents. Z equals a to the power of n becomes delta z over z equals n times delta a over a. This means exponents act as direct multipliers for fractional error. If you square a physical measurement, you strictly double its percentage error. Solving for the unknown variable is incomplete without mathematically bounding the exact size of the shadow cast by its inherent uncertainty. Let us review the complete pipeline. Everything starts in the physical world, where the mechanical limitations of an instrument define its least count. That least count dictates exactly how many significant figures can be legally recorded on the page. Multiple readings are then processed into a mean value to isolate and mitigate the impact of random error. Those finalized inputs are then passed through the strict rules of error propagation to calculate the compounded doubt during algebraic operations, which brings us back to our opening calculation, 12.35 plus 4.2. Rounding the result to 16.6 is not a suggestion. It is a strict mathematical requirement dictated by the least precise decimal input. For a student entering competitive problem solving, this is the standard. You must track physical limits just as rigorously as you track algebraic variables. A true physicist does not deal in absolute perfect numbers. They deal in precisely calculated probabilities and rigorously bounded uncertainties.
To master physics at the IIT JEE level, you are expected to navigate a complex architectural structure of rules, laws, and variables. Mechanics, thermodynamics, gravitation. Each domain comes with its own dense catalog of formulas that you have to internalize and deploy under severe time pressure. But if you strip away the surface variables, you reveal a simpler, underlying structural code. Every physical quantity in classical mechanics is built from just 3 foundational blocks: mass, length, and time. We represent these blocks with the brackets m, l, and t. The actual dimensions of a physical quantity are strictly defined as the powers to which these fundamental base quantities are raised. This structural code is independent of the units we invent to measure it. You can measure a distance in meters, inches, or light years, but its physical nature is always exactly one dimension of length. This universal code obeys a strict law, the principle of dimensional homogeneity. It dictates absolute structural symmetry across any equal sign. You cannot equate two things that are made of different base components. Mastering this symmetry provides a method to verify your work. It acts as a primary diagnostic tool for checking unknown formulas or complex algebra before committing to a final answer. An exam sheet might list 20 different dimensional formulas to learn. However, if you understand the derivation path, you can reconstruct any quantity from its physical definition as needed. This chart maps the mechanical universe starting from our 3 base pillars: mass, length, and time. By combining length divided by time, we derive our first compound quantity, velocity. Since time is in the denominator, its power becomes -1, written as Lt to the -1. Taking the time derivative, meaning we divide by time again, moves us down to acceleration, Lt to the -2. Applying Newton's second law, we multiply this by mass. This yields force, constructed exactly as mLt to the -2. Force is the critical pivot point. If you memorize exactly one-dimensional signature for classical mechanics, it should be force. Most higher-order concepts are built directly on top of it. Applying the definition of work, force multiplied by distance, our force block absorbs an extra length dimension, cascading to work and energy, ml² t to the -2. Dividing that energy block by time yields power, ml² t to the -3. This side-by-side calculation reveals how different operations yield the same result. Take momentum, mass times velocity, versus impulse, force over time. Broken down to base dimensions, both result in the exact same output, nLt to the -1. They are structurally identical. Internalizing this tech tree means you can generate the dimensional code for any mechanical quantity in seconds, directly from its physical definition. Physical addition operates on a strict rule. You cannot add a mass to a length. For any equation to be valid, every term being added or subtracted must represent the exact same physical nature. This kinematic equation for displacement allows us to test this rule in practice. Let's break this equation down into its 3 distinct additive terms and analyze their underlying structures. The left side is displacement, which is a measure of length. Our first additive term is initial velocity multiplied by time.
Velocity provides an inverse time dimension, which cancels with the multiplying time dimension. The result is pure length. The final term combines acceleration and time squared. The numerical constant, 1/2, has no physical dimension and is ignored in this analysis. The inverse time squared from acceleration cancels with the time squared, leaving us, again, with pure length. Pure numbers and numerical constants carry no dimensional weight. They are invisible to this verification system. Because length equals length plus length, the structural integrity of the equation is verified. This serves as a reliable check for your derived answers. We can take this logic a step further, using dimensional homogeneity to determine the relationship between physical variables, even when we lack the specific formula. Consider the time period of a simple pendulum. We know it depends on the length of the string and the acceleration due to gravity, but we need to find the specific mathematical connection. We set up a generic algebraic equation. Time period equals a dimensional constant k multiplied by length to an unknown power a and gravity to an unknown power b.
Next, we translate these variables into their dimensional brackets. Time is t, length is L, and gravity, being an acceleration, is Lt to the negative 2. We then distribute the b exponent across both the length and time components of gravity. Combining the length terms allows us to consolidate the right-hand side into a single expression. We now enforce the principle of dimensional homogeneity. For this equation to be valid, the total power of length and time on the left must match the total powers on the right. Since there is no length on the left side, its power is 0, meaning a plus b must equal 0. For time, the power on the left is 1, meaning negative 2b equals 1. Solving the algebra reveals that b is negative 1/2 and a is positive 1/2. This results in the reconstructed relationship t equals k times the square root of L over g. By applying the rules of dimensional homogeneity, we identified the specific proportional relationship between length, gravity, and time without needing to run a single experiment. Comparing our derived formula to the actual equation reveals this method's limit. Dimensional analysis is completely blind to numerical constants like 2 pi. The system also fails when confronted with trigonometry, exponentials, or logarithmic functions, which require dimensionless arguments. Furthermore, since addition and subtraction both simply require identical dimensions, the system cannot tell you whether to add or subtract two terms. The method produces overlapping results. Two distinct physical phenomena, like linear work and rotational torque, share the exact same structural footprint. Finally, properties like structural strain or the coefficient of friction exist outside this framework because they are dimensionless ratios. Dimensions are the mandatory structural outline for any physical system, even if they do not provide the complete mathematical story. Understanding these dimensional codes, both their utility and their strict limits, provides a consistent method for evaluating physical equations. It is a vital check for navigating the high-stakes calculations of the IIT JEE.